The central limit theorem says that the sample mean has a normal distribution. The result of this is that the t statistic follows a t distribution. And that allows us to test hypotheses concerning the population mean. But what if we're interested in something other than the mean? Maybe the median or the standard deviation or the maximum or some other parameter of the population. The t-test only works for a mean, but there's a technique called bootstrapping that allows us to estimate the sampling distribution for any statistic. And it's actually a pretty simple technique. In general, the only information you have about the population is contained in your sample. The bootstrap resamples from the original sample. We draw a sample from the original of the same size as the original by sampling with replacement. If we do this over and over again and calculate the statistic of interest each time, it gives us a bootstrap distribution for the statistic. We can use this distribution to construct confidence intervals and perform hypothesis tests. Here's a simple example. I have a sample of 11 dog weights, and I'm interested in the population median. I want to construct an estimate of the sampling distribution of the sample median. Then I can perform hypothesis tests concerning the population median. I have this sample of 11 dog weights, and what I want to do is resample from them. I want to make another sample of size 11. I can sample with replacement, which means I put back each item after I've selected it. So the same item can occur more than once. I have to sample with replacement because if I draw samples without replacement, I'd get the same 11 numbers every time. Here, I've drawn one resample, and this is what it looks like. The median of this is 47. I want to keep track of the medians of the resamples. I want to get a distribution for that statistic. Here's another resample. This time, the median was 41. A third resample. Now the median is 32. So I keep resampling like that until I have a lot of them, at least 1,000. Here I did 10,000. After 10,000 resamples, the distribution for the medians looks like this. This is what we call the bootstrap distribution. In this case, it estimates the sampling distribution for the sample median. Recall that the sampling distribution gives you the probabilities for every possible median we could draw from the population. It's usually impossible to get the entire sampling distribution. This bootstrap is a clever way to estimate it. Here's a histogram of the bootstrap distribution. I had a pretty small sample here, so there are a lot of gaps, but that's just how it goes. There are a few ways to get a confidence interval with a bootstrap distribution. If it appears normal, you can use a normal approximation. The formula for a normal confidence interval is sample statistic plus or minus a z critical value times the standard error. For a 95% interval, this z star is 1.96. That's Q norm 0.975. We can get the standard error by taking the standard deviation of the bootstrap values. And the sample statistic is the original sample median, which was 41. The 95% confidence interval from the normal approximation is 30.36, 51.64. Another way to get a confidence interval is to use the percentile method. You can use this method whenever the data is unimodal. It doesn't have to look normal. We're trying to find the least likely parts of the distribution. When data is bimodal or multimodal, the process of determining the least likely parts is more involved. But with the percentile method, we simply find the middle 95% of the distribution. We get the 2.5th percentile and the 97.5th. Using R's quantile function, the 2.5th percentile is at 32 and the 97.5th is at 53. Based on this, I'm 95% confident that the population median is between 32 and 53. Note that this interval is often not exactly 95%. What happened here is these bins are all the same number. If our interval goes from 32 to 53, we'll be cutting out these parts here, but these don't contain exactly 5% of the data. In this case, the 95% interval turns out to be more like a 98.76% interval, but it's not that big of a deal. Remember that these are all estimates. Our estimates are only as good as the data we have. We can use this distribution to perform hypothesis tests. Say my null hypothesis is that the median weight for the population these dogs come from is 52 pounds. My alternative is that the median is not 52 pounds. A confidence interval corresponds to a two-sided test. We can use the interval to determine the result. 52 is within the 95% confidence interval. At the 5% significance level, we fail to reject the null hypothesis. We cannot conclude that the population median dog weight is different from 52 pounds. Now, I'm going to change the alternative to test to see if the median weight is less than 52. I can't use a confidence interval to test this, but you could go about it using p-values. If you want to use the bootstrap distribution to estimate a p-value, you need to shift the distribution. A p-value is the probability of getting something at least as extreme as what you observed if the null hypothesis is true. We need a distribution where the null hypothesis is true. The median of this bootstrap distribution is 41. Under the null, it should be 52. So we can add 11 to every element and shift everything up by 11. And I've done that here. Now the median is 52. The probability of drawing a value of 41 or lower from this distribution is 0.0059. It's the probability that the value you draw comes from this bin here. The p-value according to this bootstrap distribution is 0.0059, which is less than 0.05. We reject the null hypothesis and conclude that the population median is lower than 52.